So fiber optics is basically the fundamental technology that we use to deliver data anywhere. So it's used for transmitting data. And in fact, you're seeing this video like a millisecond after it's uploaded at your screen because of fiber optics, because they transmit data from my computer over hundreds of kilometers to your computer. So in this video, I want to kind of go over why. So if you don't know, fiber optics uses light to deliver data. So why do we use light? How do we transmit light over such fast speeds and over such, long distances without losing any power? And what are some design considerations from an engineering perspective when working with fiber optics and communications? So, to start this off, we want to think about why light, right? Because, I mean, historically, we've always understood electricity really well, right? So, the natural decision is obviously to go with electricity. So why not? Well, the issue with electricity, despite how much we know about it and how we have transformers that could supply it over long distances, is that it comes with resistance. The first thing you learn when you study electricity is V equals IR, right? And that tells you that there's always some resistance for any voltage you supply. This resistance compounds over distances, It's a material property and there's no way to avoid it. Now, light, on the other hand, right? Light has no resistance. It's not inherent to it, right? So you will come across some forms of attenuation. So that's something you'll come across if you're an optical engineer. But that's more just the light leaking into other materials. But it's not lost in the path. So if you could design the fiber optics correctly so that there's little attenuation, then you have no resistance that compounds over long distances. That's what makes fiber optics so powerful. You can send data from my screen and it can get transmitted super fast, in the scale of terabits per second, which is very, very fast. And you'll get it at your screen with 0 bits lost, zero information lost. So now that we understand why we use light, because it's so reliable, how? Because we've all experienced encounters with light in our own lives, right? So, for example, if we want to build this intuition from ground up of how light works, so that we can then figure out how to confine it within these fibers. You can think of a mirror, right? So if you think of this mirror as this material property, right? When light hits it, it fully reflects. That's why you see a reflection of yourself. So we know that light can encounter certain objects and bounce off, right? We know that light exhibits this property. Similarly, if you've seen a window before, which I hope you have, you know that not only can light bounce off, but it can actually go through. That's why you're able to see what's on the other side of the window, even though it's like a fully, there's no holes in the window. It's just that light can go through it. So it transmits through the material. And finally, not only can light go through a material, but it can actually bend. So if you've ever encountered like a straw in a water cup, you'll see that it seems to be bending in the water. And that's not the straw bending, it's the light. So this third property is kind of what we'll focus on the most, the bending of light as it encounters a different material or medium. So it'll go in at this certain angle, right? So we think of a certain angle that it's going in at. And then on the other side, so I'm just drawing this line so we can see the angle. And on the other side, it might like bend a bit, right? So these two angles are not the same. And that's what we call refraction, light bending, right? So why is this important? Well, basically, the way we want to design fiber optics is that if you have this super long fiber, and the fiber is just basically the material of the cable, you can think of some arbitrary cable, but we want to send bits in here, go through hundreds of kilometers, and get it out here with no loss, right? I mean, ideally, no loss. Um, yeah. So how do we do this? Well, when you shoot light in, right, it's going to be coming at some angle. You're obviously not going to have a fully straight wire. So it's going to encounter the edges of the fiber at some point. And what we want to make sure is that it's basically fully reflecting off. So when it hits here, it bounces back. It hits here, bounces back, and all the way till the end. So that whatever bits you're sending in are coming out exactly the same. Now, what did I say before? You can encounter some attenuation, right? What attenuation means is that if you don't design the fiber properly, so this is your job as an engineer to design the fiber so to prevent this from happening. But basically, when you send the bits in, it'll hit the wall at some point, and maybe some of it will bounce back, or some of it might go through, right? Like a window or like water. It might bend. And these are the our bits lost, right? You're losing information here. If even one bit goes through the material, and we know light goes through materials, then you're losing information. So we don't want this to happen. We have to design so that nothing goes through. So to understand how to do that, we're going to go over Snell's law of refraction. So Snell's law of refraction is a very simple law, but it basically tells us how light bends or goes through a medium that it interacts with, right? So the way we model this is, again, we think of light as this ray. So all of this has to do with ray optics. This is a field called ray optics, in which we model light as a ray, so a straight line, right? And that's important because there's other ways to model it that we'll go over in other videos. But for here, all we need to do is think of light as this straight line that can interact with different medium, right? So this is our medium 1, and a medium could be anything. It could be air, water, wood, whatever. And this is medium 2. So what happens is we shoot light, right, at some angle. It doesn't matter if it's going in this direction or this direction. You just flip the image around. But it's going into the interface between the two mediums, right? So at the interface, something happens, right? So what's important for Snell's law of refraction, and I'll tell you what the law is, but I first want to give this visual image, is we have a certain angle with respect to this, like, whatever, normal to the interface. We have a certain angle that the incident ray is at, and that might not be the same. It could be the same. If these two medium are the same, then these angles will be the same. So theta 2 equals theta 1. But if they're not, then you could have a different thing where this bends away from the normal. So that's what we would say. And then this angle, theta 2, is bigger than theta 1. Or it could be smaller than theta 1, and so forth. So every medium, and as you can kind of guess that there's some form of property, there's a medium property, right, that decides this, because what is causing medium 2 to change the angle? There's some form of medium property, and this is known as the index of refraction. And we denote it by n. Now the index of refraction is a property for every sort of material. So glass has one, air has one, different kinds of woods have one, water has one. So each of these have their own index of refraction, right? And the idea is the index of refraction, I mean, it has several definitions you could think of, but it's basically saying how light slows down when it gets into an interface. So the way we can calculate it is we basically take the ratio between the speed of light in a vacuum, which we denote as c, and c is like roughly 3 times 10 to the 8 meters per second, and that's the fastest speed of light you can get. That's the fastest anything can get in the universe. So we have c, and it's basically the ratio between the speed of light in a vacuum, so vacuum, over the speed of light in the medium. So the index of refraction for glass will be the speed of light in vacuum over the speed of light in glass, right? So for starters, we know that V is always going to be smaller than C, right? Because the vacuum is always the fastest. What this means is if V is always smaller than C, N is at least equal to 1, right? Because either V is equal to C, if we're talking about the index in a vacuum, then you have 1. And if this is less, then n will be more than 1, right? So basically, the larger n is, the slower light is in that medium. Okay? Now you might be thinking, what is this useful for? I mean, fiber optics doesn't really use any sort of like water or anything. But the point is, if we can manipulate these mediums so that light is not only not going through, but actually fully bouncing back, then we can design fiber optic cables. So how do we do that? So basically, there's a relationship between the angles of the rays. So there's a relationship between the angles of the incident and transmitted rays and the indices of refraction. So the index of refraction. And this is what we denote as Snell's law. Basically, if you have medium 1 with an index of refraction denoted by n1 and medium 2 with an index of refraction denoted by n2 and similarly theta 1 and theta 2 for their angles, then we say that n1 times the sine of its angle is equal to n2 times the sine of its angle. Now this is interesting. I mean, at first you might think like, well, what does this mean? But it's basically saying that there's an explicit way to predict what the angle of the light will be in each medium based on their indices of refractions. And these index of refraction values are known for everything. So like, glass might be like 1.4. I don't remember the exact number, but they have numbers in a table you can search up. And so you could always predict the angle that light will refract at. So for example, I mean, if n1 is equal to 1 and n2 is equal to 2, right? So 1 just means it's in a vacuum. And we know that light is going in at whatever, theta is equal to 45 degrees. We know what its angle is going to be on this side, right? Because sine of 45 degrees is 1 over root 2, right? So 1 times 1 over root 2, I'm just plugging in the values into n1 sine theta 1, is going to be equal to n2, which is 2, times sine of theta 2. Now you have one variable here, so you can move this to the other side. You get sine of theta 2 is equal to 1 over 2 root 2, and then you just take the inverse sine, right? You get theta 2 is equal to sine inverse of 1 over 2 root 2. And so you obviously, it's not easy to tell without using like a calculator a lot of the time, but you can use some intuition to know whether light will bend towards the normal or away from the normal, right? That's usually how we describe how light is refracting, or it could just not refract and go straight through or reflect, but we'll get into that more later. The point of Snell's law is more for when it refracts, right? And you can see how that would be useful for fiber optics because we're basically trying to avoid refraction altogether. So we can predict how to do that. But I mean, to get more into this, first of all, just to build an intuition, if we know, right, that n1 is more than n2, for example, so n1, so light is traveling slower in n1 as opposed to n2, right? There's a way to think of this visually. I don't like it the most because it's not the most accurate description of light, but it is nice if you're like a visual learner. Basically, if you think, so here we have n1 is smaller than n2. I mean, sorry, larger than n2. So if you think of light as wave fronts following the ray, then what happens? Once it crosses the boundary, and let's think of wave fronts basically as like each point travels at the same speed, right? On the wavefront. That's kind of how wavefronts work. But when you get at the boundary, then light is traveling at a different speed. So if n1 is more than n2, you know light travels faster than n2. So this part of the wavefront is traveling faster than this one. And if you know how vehicles and stuff work, you should kind of intuitively know that that's going to cause it to bend this way, right? So I can exaggerate that more, but like it's going to bend away from the normal. So if n1 is more than n2, then in n2 it bends away from the normal. And on the other side, if n1 is less than n2, then it's going to be slower on this side and faster on this side, so it'll bend towards the normal. Anyways, you don't have to think of it that way because, I mean, it's not exactly how light works, but it's a nice visual image. You could also just think of it in the sense of, you could rewrite this equation as if you just divide both sides, n1 over n2 equals sine theta 2, or yeah, actually, let's just do it like this. Sine theta 1, n1 over n2 is sine, so I just divided by n2. If n1 is larger than n2, then this is greater than 1, right? Which means sine theta 2 is going to have to be bigger than sine theta 1. And the thing is, we're never getting more than 90 degrees since this whole place is 90 degrees. So if you think of a sine wave, up until 90 degrees, it's increasing with theta, right? So basically, as the sine increases, theta also has to increase. So that's more of a mathematical way to think of it, but basically, if n1 is bigger than n2, theta 2, or sine of theta 2, has to be bigger than sine of theta 1, okay? It's kind of like an inverse relationship. Anyways, I think you got the point. You could play around with that a bit more if you want. But that's how Snell's law of refraction works. Now, you might have noticed we still haven't really talked about reflection, right? We've talked about refraction, but not reflection. And reflection, as we talked about before, is what we want in fiber optic cables. In fact, we don't want refraction. So let's think about this a bit more from the Snell's law perspective. Because there's something interesting that happens, and you might have picked it up as I was talking about it. But basically, we have these two mediums, right? Again, let's say, again, n1 is bigger than n2, right? Now, same kind of setup. We're going to go with some form of theta. And by now you should know that because n1 is bigger than n2, theta 2 has to be bigger than theta 1. So it's going to bend away from the normal. Theta 1. So, well, this is interesting. What if theta 1 becomes bigger? Then, it'll bend more, right? And it'll bend more. And eventually, you can imagine that it's going to get to a point where it's at 90 degrees. It's fully bending towards the boundary. So what will Snell's law tell us about that? So when theta 2 is 90 degrees, because clearly we can see from this visual picture that that's the maximum it could go, and we know that it'll get to that point because it has to be bigger than theta 1, then what happens? Well, we said that sine theta 1, n1 over n2, is equal to sine of theta 2, which is 90 degrees. Sine of 90 degrees is 1, right? But this is more than 1. So that means theta 1 could keep going, right? We basically have this thing where, based on the equation, I mean, we have some angle for this, but technically theta 1 is not at 90 degrees, right? Theta 1 is a bit less, so maybe theta 1 is like at here. But what happens if we keep pushing it? Then this equation no longer holds. So, for example, when this is at 90 degrees, let's say theta 1 is at 90 degrees, then we have 1 times n1 over n2 is equal to sine of theta 2, right? But sine of theta 2 can never be more than 1. But we know this is more than 1. So this equation doesn't hold. Something is happening. We're having some form of contradiction, and that's not good. So how do we explain this? Well, basically, at this point we talked about sine theta 1 n1 over n2 equals 1. We've pushed theta 2 to the limit. We've pushed theta 2 to 90 degrees. That's the limit for theta 2. We can't go any more than that. So what happens? Well, there's a name for this. Basically, what we say in ray optics is when theta 2 reaches 90 degrees, then you're at that limit. You've reached the critical angle. So what does that mean? It means that theta 1 in this case, so sine of theta 1, if we just rearrange this equation, is equal to n2 over n1, right? So theta 1, which is equal to the sine inverse of n2 over n1, is our critical angle. This is a specific angle based on the material properties that you basically can't go past. You can't go past this angle. So you can't get larger. Why? Because then the equation no longer holds. So what happens to the ray if we shoot it at an angle large? So what happens if theta 1 is more than the critical angle? Then we have a phenomenon known as total internal reflection. Because we know we can make it bigger, right? Like in the case before, if n1 is like 2 and n2 is 1, theta 1, theta c might be like way less than 90 degrees. So what if we push theta 1 past the critical angle that makes theta 2 theta 2 90 degrees? Basically, all the light reflects. All the light reflects. This is what we want. This is what we've been looking for. In fiber optics, we want all the light to reflect. And now we know how to get to that point. If we keep pushing with a big enough angle, so let's say this is the critical angle that makes basically this ray go right up to 90 degrees. If we push at an angle bigger than that, this can't go any farther. It's going to reflect. And it's going to reflect at the same angle that was incident on it, you know, because the medium is the same. So it's fully going to reflect. And that's what we want from the fiber optic cable. Basically, the way it works is we design this fiber optic with some properties. We design an outer layer, which we call the cladding, and an inner layer. I mean, it's much smaller than this. And the inner layer is what supports the light, and we call this the core. In a step index optical fiber, we have two materials. So the material step. The reason I call it step index is because there's some more complicated formats in which the materials aren't uniform. But in this form, we have N, the index refraction of the core, and the index refraction of the cladding. And there's a way to design it, which I won't go into detail right now, but in future videos, where you basically make the index of refraction of the core slightly larger than the index refraction of the cladding. In a way, so that if you shoot light in at an angle more than the critical angle at the very beginning, then it'll completely reflect through all the way, because it'll reflect with the same angle that it's shot in, so it'll have total internal reflection again, and the same angle again, and so forth, all the way to the output. And so basically, by manipulating the materials you use, so the core and cladding are made with these specific materials of glass that allow for total internal reflection, and it's abbreviated with TIR, to happen at every single boundary, because it's just doing the same thing over and over again. It's just doing this, right? It's getting shot in with a certain angle, and it's getting reflected with that same exact angle. And we opt for materials that really like optimize for the critical angle we want. But basically, it allows all the light to be retained, to be absorbed at the end. And that's how we send bits of information through hundreds of kilometers at terabits per second scale by using total internal reflection. So that was the main idea in this video. In some other videos, I'm going to get into examples of design considerations and all that kind of stuff. But in this video, we just wanted to get over the main aspect, which is how does it work? Thank you.